As the world population keeps increasing, more stress is being placed on the limited resources of our planet. One of the major environmental issues is waste pollution from food waste. About 7% of greenhouse gas emissions come from food waste. About 20.4 comes from agriculture and land that were used to produce this food. One way of mitigating this issue is recycling through conversion of biological waste into biogas and digestate that can be used as renewable source of energy and fertilizer, respectively. This proposed venture, biogas plant through anaerobic digestion, not only aims to make profit out of organic waste, but also aims to help the United Nations to mitigate the effects of climate change by targeting 4 of the 17 Sustainable Development Goals, such as employment opportunities, sanitation, reduce waste pollution, as well as to provide affordable and clean energy, especially to the slum communities in India.
In the biogas industry, there are different types of anaerobic digester designs, such as a covered lagoon, PFRs, and CSTRs. Compared to other configurations, the CSTR provides greater uniformity of system parameters, and thus is preferred. As the reaction occurs in the liquid phase, the biological waste must be processed into a sludge of approximately 90% water to be fed in the biodigester regardless of the type of feedstock. Then the sludge is pumped on a daily basis in the reactor where an optimal residence time will allow for good conversion to biogas. Then the produced biogas is then sent to an absorber in order to remove impurities such as hydrogen sulfide, which smells like rotten egg and is very toxic and corrosive, and must be removed to the highest extent possible.
As Nicholas mentioned, our system will support a wide variety of substrates. Our simulation adapted Dr. Rajendran's process simulation module, which sampled many components that are found in biological waste.
Here is a schematic of our design in order to meet the standard methane purity of 98%. Notice that the flash methane is being flared in order to meet air quality regulations.
In order to predict the biogas production in a digester, the module consisted of 13 hydrolysis reactions. 33 kinetic-based reactions were specified for acetogenesis, acetogenesis, and methanogenesis. These figures are scheduled for food waste, where the darkened squares show the month in which the type of fruit or vegetable waste was found. Using this figure as a guide, we sampled a heterogeneous mixture of vegetable waste, primarily composed of vegetables with more darkened squares.
As the Aspen model takes components input as a 1x61 matrix, a MATCAD file containing 1x61 matrices was made in order to specify the digester feed compositions for cow manure, human feces, vegetable, and citrus waste based on literature search. This sheet also allows us to specify our feed composition based on the sample components.
So in order to establish a basis for all substrates, we initially in a 10,000-liter reactor conducted a sensitivity analysis using cow manure. The gas production for key components like methane, carbon dioxide, hydrogen sulfide, and water were observed by varying flow rate. Smaller feed flow rates allowed higher residence time, which leads to a higher methane mole fraction and an overall lower methane mole flow rate from the reactor. For any substrate, a methane composition of 45% was set as a target because it was high enough for a simple separation process with a good amount of substrate converted into methane, but also low enough where a good amount of methane is being processed per day. The figures here show that even though the initial flow rates for the reactors end up being similar in magnitude, some substrate produce more gas than others. Rotten vegetables had a higher purity at 51%, but in terms of raw gas production, it is almost the same as cow manure, but with a higher efficiency. By way of comparing substrates, we used the production ratio as a way to normalize the amount of kilogram of substrate needed to produce 1 kilogram of raw gas. The lower the number, the more efficient the process was. Human feces had by far the best efficiency, while vegetable waste had the worst. We also analyzed the possibility of using either water or triethylene glycol for scrubbing. Using effluents from the 10,000-liter digester, water and glycol both achieved 98% methane purity, but water achieved the target with a higher recovery. From the optimization, 20 stages were chosen for the glycol scrubber, while 8 stages were chosen for water. A pressure drop of 1 bar for glycol and 4 bar for water allowed the gas to reach the purity of 98%. If we compare the product purity versus absorbent between the substrates, the figures here indicate that with a lower absorbent mass, water was able to scrub the vegetable and human mixture best, followed by the rotten vegetables as compared to glycol. In these figures, the y-axis represents the mole fraction of water in the product. Glycol with 1% water content was able to dry the product 5 times more than water. This is desirable for gas that's intended for pipeline in developed countries. Another advantage is that the higher boiling point of glycol than water allows the flash at higher temperatures to get rid of most of the components with ease with little absorbent loss, and thus has positive environmental impacts. We used the absorbent to inlet ratio to compare the ease of cleansing for each substrate. The term states how many kilograms of absorbent we need to clean 1 kilogram of raw gas flowing in. The average was about 7.3 for water and 12.6 for glycol at the target purity. This helped establish the advantage of using water for scrubbing. Overall, the vegetable and human feces mixture seemed to outperform the individual substrate because it was easier to clean with the water absorber. It yields a slightly higher recovery and has a better production ratio. These findings were further investigated in Design B.
In this design, instead of feeding the digester with one pure substrate, we will be feeding the same mixture into all the digesters. Potentially, the proper mixture of all the components could yield better results than if we fed those same components into digesters separately. There are 4 variables studied in these mixture ratios: product flow rate, production ratio, methane recovery, and ease to clean. Product flow rate is the final amount of purified gas that we are yielding, which is where our profits come from. Production ratio is the amount of inlet required to make 1 kilogram of raw gas. This serves as a way to quantify how efficiently we are using our biomass. Methane recovery is the amount of methane that we collect in our final product compared to the methane coming into the scrubber. The more recovery means more yield and less methane to deal with environmentally. Finally, ease of clean is the amount of water absorbent we need in the scrubber to clean 1 kilogram of raw gas entering. The less water we need, the less dirty water is required to be dealt with downstream. To make the optimization easier, only the human waste and raw and vegetable ratio was varied, while the cow manure remained at 10%. This is an industry standard and serves to fuel the digester with the required bacteria. To quantify the improvement of mixing substrates versus leaving them pure, a deviation percentage was calculated for each variable. This is the percent deviation of the actual simulated values from the expected values. Any positive deviation means that the mixture serves better than the 2 substrates reacted alone. The expected value were calculated 2 ways, with and without considering the effect of cow manure. The equations for each are shown above. The results for the variables are shown in these slides. After careful consideration of all the results, we concluded that a 50% raw and vegetable mixture was our chosen ideal mixture. The only variable that showed an optimum without the deviation analysis was the product flow rate, which proved to be max at 55% raw and veggies. We considered that the graphs without the effect of cow manure were more important, as the cow manure percentage was already predetermined. With our mixture, we obtained a 27.53% increase of product gas yield compared to the substrates being reacted alone. More details about how we decided on the mixture can be read in our report. The table in the slide summarizes the optimum mixture ratio for each variable and its corresponding value.
To assess the economic profitability, the venture profit, return on investment, and payback period were calculated while considering cost. It was decided that the biogas methane will have a selling price of $3.78 per kilogram, and the digestate price will be less than $1 per kilogram. By analyzing the profitability of pure substrates, namely cow manure, human feces, and rotten vegetables, as well as a mixture of 50-50 human feces and rotten vegetables, it resulted that human feces generates the highest net profit of about $1 million USD, yielding the highest return of investment of 506% and resulting a payback period of 0.03 years. In order to profitably compare Design A and Design B, the economic costing and analysis of pure substrates mentioned in the previous slide for Design A were combined linearly. This was done by designating 2, 3, and 3 reactors out of 8 total reactors to be fed by pure substrates, respectively. In Design A, comparing the water to glycol scrubbers economically, it was discovered that the return of investment for water scrubber was higher than the glycol scrubber, yielding to 290% and 276% respectively. The final optimized mixture in Design B, containing 40% human feces, 10% cow manure, and 50% rotten vegetables, resulted in an overall higher profitability as compared to Design A, yielding to an ROI of 394% and payback period of 0.03 years, resulting in a healthy venture profit.
As my team members have shown, our process is easy, reliable, and eco-friendly. Here are our final recommendations. The feed-solid ratio should be kept under 10%, diluted, and heat pre-treated. It is best to use a water scrubber since it will have a higher yield of return on investment. The optimal feed is 40% human feces, 10% cow manure, and 50% rotten vegetables, and the government should give out more incentives, loans, and grants for sustainable energy. This project, if implemented, will help people all over India, especially those impacted by waste and in rural areas. It will create job opportunities and help the environment. As engineers, we should strive to innovate for greener technology, since the Earth is the only thing we have in common, and we must protect it. Thank you so much for listening to our presentation. We hope you enjoyed it. If you have any questions, please let us know.